All right. I need it. So I assume that you all did set up LAYNII from, for example, by following the README file on GitHub, or by checking out layer fMRI LAYNII -setup. And on the summer course site, I also linked the layering example data set that I will go through. If we have time and you want to do it on your data, that should be fine too. So the overall goal here is to take any like nifty data set, for example, directly functional data, even though Farouk just told us that we shouldn't segment in functional space directly, we will do so anyway. And then extract a layer profile for it. So I downloaded the data right here in the v1_layering example. I hope that you have access to that too, and you are kindly invited to follow everything like I do it. In fact, I think the entire pipeline will not take me longer than 10 minutes. And I'm kind of counting on it that you are doing it along with me. And if you have trouble, then we do it, solve it together. So maybe I start by describing the data that you hopefully have downloaded. So this is EPI with almost 0.5 millimeter resolution. This is just a mean vaso image, and in vaso, different to like conventional gradient echo bold, we have a stronger T1 weighting in there. So it doesn't really look like the data that Farouk just showed with like big vessels in there. You might have hints of those vessels here, that the very, very big ones, and maybe even like that inflow effects from large arteries, maybe these white spots here and there. And for example, also here. However, it's mostly a so-called anatomical contrast. So it looks comparable to like MP range or MP2 range, in fact. So this is the, maybe I open it in FSL view, or FSLIs for that matter, so we can browse it a bit more. So this is the mean image of the functional data. And this is acquired at Neoterra scanner. So the attendees from Liège might be easily able to reproduce these kind of data. However, they are natively very noisy. So here I think I acquired 5 runs of at 14 minutes block design tasks. And I will just adjust my windowing here to make it look a bit more pretty. Maybe not so much. All right, and I'm particularly interested in the visual cortex here. I'm not sure which slice I should focus on. Maybe this one is good enough. So here we have the calcarine sulcus. On that side, maybe you can see it right over there. And on the right side here, you should see it too. Maybe if you want to see it and you're kind of used to look at those kind of noisy data, you might be able to see that there are bright voxels here between the gray matter border and CSF. Then it gets kind of darker, and then it becomes bright again. The bright stuff here obviously is white matter, and the kind of these maybe 10 voxels forming a line over there are referring to the increased or reduced iron and increased myelin of layer 2-3. The dark stuff refers to the so-called sphere of Gennari. And I can load in the functional data, and now, which should be in the same folder, for example, the bold ACT nifty, which looks somewhat like that. So I can threshold it and make it colorful, so you see how that usually looks. So in bold, as we have talked about, you usually have a strong activity at the cortical surface, and then it kind of decreases down towards the towards the cortical depth. And very often, even like at the border between gray matter and white matter, the sensitivity of bold is so low that you often don't exceed the detection threshold. As an example here, we also acquired a vaso, which we can use as different contrasts right now, or as a toy model of simulating different functional contrasts. which is the same thing. It's just a bit noisier and has a slightly different activation pattern. That's it's not so much dominated from the superficial layers. It's more the deeper ones, and you can kind of see that it mostly spares CSF as opposed to, for example, the bold, which is a bit more blobby, like there. Okay, so now we are interested in looking at these activation scores and plot them across cortical depth. And as Farouk already alluded to, we need a good segmentation for that. So I would like to show you how I do this in FSLIs. And in case anybody of you does not have FSLIs, we can do the same thing again for FSL View or IDK Snap or something. So let's just focus on one sulcus and quickly manually segment this in EPI space. In FSLIs, I do so by clicking the, I'm not sure if you see my video, I click the Alt and the E key on my keyboard, Alt and E. As soon as I do that, I'm in so-called edit mode. Maybe there's something here. If you go to Tools and then click edit mode, then you now have two new bars. And the first thing I do is I generate a new file, for example, by clicking this button. So now down in the list of all the files that I have on top of each other, I have now something that's called vaso_mask. So it basically copies the name of the previously top part of the queue here and adds mask to it. Now we can have a new data set that has the same dimensions, with the same resolution, same matrix size and everything. It's just empty. So as soon as I go through anything here, you might see that it's all just filled with zeros. So the purpose of the segmentation is now to segment the gray matter and in fact prepare it in a way and do the segmentation in a way that later we can do the layering easily. So we have this edit bar over there, so we can draw, for example, by clicking on the draw pen. And I'm not sure how well this comes across on your screens. And the top field here is the selection size, where the default is 3. I want to change it to 1 to be mostly accurate. And I also change the color maybe to green with windowing between 0 and 3. So now we can just draw kind of the surface here. So anything that's between gray matter and CSF. And you can already see that we are kind of limited by resolution. And if we have time, I will talk about strategies to kind of avoid this kind of jaggering space of this kind of being limited by the voxel space. So I'm just following the cortical ribbon. Maybe this should be still the borderline. I'm usually conservative and make the borderlines between, for example, here, gray matter and CSF further towards CSF, because later you can cut it always. And I rather draw the borderline slightly above gray matter. Similarly, for a white matter, I change the fill value now from 1 to 2, and then follow the cortical ribbon at the borderline between gray matter and white matter. Just follow the ribbon over there. Again, I'm trying to be kind of biased towards white matter, and then can later cut it in the profiles anyway. And at this point, I want to stop and maybe ask back if anybody has trouble doing the same thing, or if you are not doing it anyway and then just look how I do it. Can you give me any feedback? Does it work for you?
It's fine, and you were right about the graphical pen. It's much better.
All right. Okay. Cool. All right. So now we have the surface drawn with value of 1, and the white matter, gray matter boundary drawn with a value of 2. Now let's fill it up, for example, with a value of 3. So what I do there in FSLIs, I change the fill value to 3 and just close the gaps on both ends, because FSLIs has this kind of filling feature in there by not clicking the drawing tool, but the filling tool, selecting this button. And filling voxels that are next to each other, and not crossing borders. So I select this button, and this button, and now I just click it, and it fills everything that is within this closed area. This is now only highlighted, so it's kind of transparent. I execute it by pressing this button over here, the fill. And basically, that's the segmentation of how I want it. And now I can save it, for example, by clicking this little disk button. And I usually save it as rim.nifty. So let's save that. And I already had one. So I just call it rim1.nifty. All right. Is there anybody who uses FSL View or ITK Snap? If so, please let me know, then I'll do the same thing in those viewers.
ITK would be nice.
Yeah, exactly. ITK would be nice. Thanks.
So again, I'm opening up the mean VASO, and now with ITK Snap. And there we are. I'm never really sure how to adjust this. I think inspector.
Control J.
All right.
Oh, yeah, or this one.
Yeah. So let's zoom in here. I forgot which slide we. Anything? Yes.
Go more posterior.
There we are. So that was our sulcus. There's this little drawing tool. This is now the brush size. I want to have it as small as possible. And I want to draw with ones. So I was too fast. So I selected the drawing tool here, or the paintbrush mode, as they call it. I changed the brush size to be as small as possible and selected label 1, because the software suite that we are using expects values of 1 to be indicative of the cortical surface, and layers values of 2 to be indicative of the white matter, gray matter borderline, and values of 3, anything in between. And if you have different values, that shouldn't be a problem. Farouk wrote a program, so-called LNRimify, which will circulate, permutate those, and generate them in the way that they can be used in LAYNII. So now I'm just doing the same thing, just filling it up. I'm lazy, so I'm just filling one side here with value of 1. Then I have the value of 2 to draw the same thing on the white matter borderline. And then I'm doing the rest with 3s. And we talked about this in the hallway just now. In ITK, there are other tools available to fill stuff. Now I don't know how
you can select. Go here, Renzo. Wait, this is useful. Go here. Do you see my arrow?
I do. I will fill it up, and then I will.
Because there's a way to make it not fill in the voxels that are already drawn on.
This one?
Yeah, and if you go to paint over, and if you say on the clear label, it will only paint. Click on clear label. Yeah, and now just like draw a line on the red voxels. Let's say.
All right. Yeah. All right. Yeah. Makes sense. Cool. So all labels. So I will change this label back to 2. And maybe this 2. Let's save this in segmentation. Save segmentation image, I think. We can call this rim itk.nifty. All right. There are no requests for FSL view. Then I think we can continue. So now we have our mean VASO image, and we have various ways of how we drew borderlines, and we have 2 activations, which are in this case 2 different sequence contrasts, but you can also imagine having 2 different task conditions or whatever. So now the next thing that we would like to do is convert this segmentation into cortical depth labels. And in order to show how that should look like, I will open this again because I will refer to it later. And from file. So which one should we use? Let's use rim1. Why can't I? I would like to open my terminal right next to it. I will focus on I will focus on this slide and make it smaller. I think there we were. Okay. So I open a console right in the folder that I am. And now if you installed LAYNII and you type in ln_, I explained stuff like the Docker container and the VirtualBox, which is not using the absolutely latest version of LAYNII. So I'm not using the advanced version Farouk implemented, but I'm using a kind of low-key layering program. I will show you Farouk's version in a second. So if we type in grow layers, then you should see something like text like that. I'll show it again. So I just type in ln_grow layers. And I think if Miriam didn't get the sourcing right, you would type in /mount /layni/linux. So Miriam, if you type in this one, then it should work for you too. And maybe I can make the letters a bit bigger here. View bigger. No, that's the entire window, right? How can I change the font size? Defaults bigger. It just increases the window size to +++. Does anybody have trouble typing in ln_grow layers and is not seeing a bunch of text here? Okay, I don't see complaints, so I assume that it works. So now this is, for example, one program that converts these rim files into layer files. And specifically now I would like to, you can copy potential options of how this is used from up there. Namely, this program needs a rim file, and we give it with a -rim and then the file name. So rim, I think 1 we called it. We want to give it a number of layers, which in this program is given with a -N. I don't know, let's do 11 layers. And what is important, let's also give it an output name, output, because different versions have different conventions there. So let's give it output layers.nifty. If you have older versions of LAYNII, that will be the default anyway. So if we run this now, it will do all kind of growing stuff and write out a layer nifty file. So let's look at that by double-clicking the layers.nifty file. So this now is a new nifty file, and I will give it different colors now. For example, something colorful of, that's my rim file. So maybe now you can see that, I will make it a bit bigger, that it converted the rim file, which had 3 values from 1, 2, and 3 to something of 11 values, where the smallest number is the borderline between white matter and gray matter. And then as I move along, the layers increase until I end up with 11. And if I want a different number of layers, for example, if I want only, I don't know, 7 layers, this file will now be overwritten. Then everything will be scaled between 1 and 7. And the optimal number of layers is a topic of debate. It depends obviously on the number of voxels you have across cortical depth. And if I have time, I will talk about like issues of upsampling. If you want to learn more about the optimal number of layers, check out on the summer course website the blog post on which is entitled "How many layers should I extract?", where I recommend to always use as many layers as possible, even though we don't really have the resolution for it, but just to minimize partial volume effects. So now we have these layers directly in Nifty space of the voxels, and we can easily now just average the signal of the T1 signal or the Vaso signal or the bold signal for each group of voxels, like for each mask, for each value in these layers. And how I usually do this is with this script, which is called avni_LAYNII. I'm not sure if you have avni installed. This should be a rather straightforward task, however. So in avni, you have the command of 3D ROI stats. You give it a mask, and then it just writes it out. So I will execute it and show you what it does. So if I type in avni_LAYNII and give it an input file, for example, let's give it a bold file, then it generates these text files.
Did we put this to LAYNII extras, Renzo? Maybe you can.
It is definitely in the shared folder. I think
maybe we should do it, because if someone wants to have a look at the script like separately, we should push it there.
So I mean, on GitHub,
we can do it later.
Omar Farouk Gulban, I think there is a, let me see, extract.
There's something called extract layer profiles. Can it be inside there?
That's exactly
there you go.
No. It's literally just taking all the voxels where you have a certain layer number and averaging them. And it writes out a little text file where the first column is the mean value, the second column is the standard deviation, and the third column is the number of voxels within that layer. In fact, it writes out two files. avni natively does it in rows and not columns. I just transpose it. Maybe I show you what the content of that script is. It's like really simple. So here I just extract within each layer the mean and write it into layer_t dot. Then I do the same thing and write out the sigma, namely the standard deviation. And then I do it again and write out the number of voxels. And I write this as two different rows in the file. The next line here is literally just transposing it. So it makes rows out of columns. And the very last line here is also in avni. It's a 1D plot. And I just plot the content of this, this little text file that we have. And here you see the output of that plot. And the bottom row is the mean signal activity. The x-axis would be the cortical depth. Right here is CSF, left here is white matter. And as we go from right to left, we are kind of starting from the superficial layers and going deeper and deeper. The red curve refers to the standard deviation. And you can see that the superficial layers have most of the noise. The green line here refers to the number of voxels we have within the layer. And you might see that we have more voxels at the white matter, gray matter border. And this is just a feature of the geometry of our rim file, namely that we just have more blue voxels because it's a concaved structure. We're looking at a sulcus, not a gyrus. So this is not worrisome unless you have very weird statistical assumptions in comparing the different layers. And let's do the same thing, for example, with, how should we? Let's repeat the same thing with a different number of layers. So let's execute the same thing again, not with 7 layers, but with, let's overdo it and let's have 15 layers. This is really pushing it. We don't have 15 voxels across cortical depth, but still we are reconstructing 15 layers. And then extract this same profile again. So now you can see that we are already having weird issues that some layers are less represented than other layers, specifically the second to the borderline ones. The overall signal and noise characteristics are still the same. So in bold, we still see that there's higher activation at the superficial layers compared to the deeper layers. And we also see that there's more noise or more standard deviation in the superficial layers. We can try to regularize these different numbers of layers a bit by using an additional option for the layering, for example, with minus a thin. I hope this works now. And plotting the layers again, you see that especially on the right, it's a bit reduced, but we are still at the bottom of a circle, so we still have many more layers at the superficial, at the deepest layers. Overall, the signal profile still looks the same. Maybe we extract the same thing for the VASO now. So I execute the same AFNI LAYNII, but now with the VASO act again with the same number of layers, and you can see that the number of voxels is the same. So the green line is the same. The profile, however, is not completely identical. Of course, we have this jumping up and down because we have too many layers now, but it's going down towards a baseline a bit earlier, for example, than the bold. Bold is just increasing. VASO might be an inverted U shape. And we can try to repeat the same thing with less layers. Before we had a 7, I think, and do the same thing again. Where it might be a bit clearer. So in VASO we have more inverted U shape. In bold we have this more increase towards the superficial layers. Now we can do the same thing with the IDK Snap RIM file. For example, we called it IDK RIM ITK, right? I don't know how many layers we should use, maybe 11. And plot the same thing again. And also for VASO, which again, we might be pushing it because we have 11 layers and we already have this up-down jump in the number of voxels. But overall, we still see the same features, namely that in bold, the signal increases towards the superficial layers. In VASO, it's more an inverted U shape. And here we basically have one voxel that contributes to the layer number 2, layer number 1. We start counting at 0. So that's why I wouldn't really trust this point all too much. So we might have too many layers already. Maybe I can use show you how the same thing works in another program, namely the LN2 layers. But maybe I want to make a short break here and ask if you have any trouble executing LAYNII at this point, and whether or not you could generate your own layers on that data set.
Yeah, it worked.
Okay.
It worked quick and easy.
Right.
Okay,
cool.
But I couldn't, I don't have AFNI, so I couldn't do the last step.
Okay.
You don't need to do AFNI. Like, you can write your own little Python script or MATLAB script or whatever script to also like just access those voxels and plot in the way that you like. So it's like AFNI is just one way of doing it.
Do you have the text file though? No, you couldn't even extract it, right? Because you don't have AFNI. I think in FSL, do you have FSL? Farouk, do you know the FSL ROI extraction command? You know what?
I would have done it with like scripting, basically. Maybe like this might be something that we can show next time. Other ways of extracting the profiles.
Maybe we should just write a LAYNII program for it.
Yeah, that's right. Maybe. But also plotting, you mean? Oh, no, just for extracting, right?
Right, for extracting.
Yeah,
I wouldn't want to touch the Qt or X11 or so.
Yeah, just on writing a CSV file, for instance. Yeah, that's actually a good idea. Yeah, let's do that.
All right. For completeness, let's do it for those who have LAYNII versions.
Renzo?
Yes.
For me, it actually says that the ln grow layers command is not found.
Okay. This might have multiple reasons.
You can navigate to the folder of the LAYNII, LAYNII,
Yeah.
and then run the command there.
Yeah, no, I did that, but then it still gives me the same command. But I can
then put dot / at the beginning of ln.
Okay, I'll try that.
So if you don't execute the ln_grow layers, but /ln grow layers from your respective directory, from the LAYNII directory. However, then you also need to make sure that the RIM file is in that same directory.
Yeah. Or you need to give it the absolute path to the RIM file, which is starting from your root and goes until the file.
All right, while LAYNII is trying that, I will show you another way of doing things, namely using Farouk's ln2 layers with S. I just copy paste one of those. So again, we have the -rim. Let's use the same RIM file, rim1, number of layers. His default is 3. Let's use 7. Let's do it equivolume for.
Yeah, LAYNII says it works. So fine.
Okay, cool. And let's give it an output name. ln2 layers .nifty. Wait, no, it was just a prefix for Farouk. So now Farouk does a lot of things. He grows the layers, or he floods the layers, as he calls it, which is, I think, almost identical, if I'm not mistaken. He doesn't include the values of 1 and 2. He only uses everything in the RIM file that we like only the red part. And where is my terminal?
And there's a reason for it, but I think we don't need to discuss it here.
Importantly, he writes out layers as a file with the prefix that we had as output. So our LAYNII file, however, expects the mask to be named as layers.nifty. So I will just rename it with move here equivolume to layers.nifty. Maybe let's look at that to make sure that everything is all right and in order. So I renamed this one now. So as you can see, Farouk's layers, these are Farouk's layers with 7 layers. I use the equivolume now. So you see that we are pushing it too much. So for example, here the layer number 1 is only really visible at the top of a gyrus. Let's run with it anyway and extract the bold profile and the laser profile. Where am I? Over there. Which looks approximately similar. There's something weird going on at the surface because you have, like usually we have up to 64 layers, but there it really drops off, which is, I guess, the same feature that we saw earlier, that the second to the last ones doesn't have a lot of signal. So there is actually only those 2 voxels here contribute to the superficial layers. So maybe 7 are not enough, too much. Let's do the same thing with maybe 5 layers. And rename it again You can actually use the equidist now and run it again. We extract the bolt. Oh, now it looks kind of not really smooth anymore. Again, oh no, now the y-axis is going down to 44. So now we have a more equally distributed number of voxels per layers. So that's a problem with the different numbers of layers. And one way to deal with that is to simply upsample the images and subdivide every voxel into like several subvoxels. And in the folder that you downloaded, there is a script how I do this with upsample. You can do it in any other way how you like it to. For the sake of it, I will just show you quickly how I do this. Let's put this into the scaled folder. So it's upscaled. And I will navigate to that folder too, cd scaled, and upsample it. Upsample all the 3 nifty files that we have. And it basically upsamples everything by a factor of. So it basically extracts the voxel size and divides the voxel size by 3 and then writes out the same data set with a cubic interpolation by a third of the voxel size. And here, this is just changing the data type from a float to a short. Because as soon as you upsample something, sometimes the file size can be rather big. So now our new voxel size is much smaller, and I just do this with all the files that we have. I will close my viewer again because now we need to redraw the RIM file. And then
so this upsampling script is also available at LAYNII extras repository.
Did you double check it?
Yeah, I checked it right now.
Yeah, I tried to. Yeah. So now we have new files: the scaled bolt, scaled vaso, and scaled mean vaso. And for example, as soon as we open the scaled mean vaso, now we have bigger data sizes, and it looks kind of smoother because it's upsampled. We have, and we don't have these edges anymore for the different voxels. Oops. But it's literally the same data. It's just upsampled. So I will very quickly now draw layers again. I generate a new file, which should be there in a second. And then I select my pen, make the size 1, and quickly draw it. And now you see I can also draw much smoother. And I'm lazy, so Farouk, forgive me for all the segmentation errors here.
Yeah, this is by the way, the reason why I do not include the border voxels, because when there are like, let's say some weird lines in the border files, which did happen here, as you can see, there, I just do not include this border label voxels to the layering. I mean, you can include them later anyway in the post-processing by drawing the values, looking at the RIM data. maybe something for a future blog post.
Or maybe also like to have it optional in the LN2 layers to include them.
Yeah, that's right. Yeah, I was this time I was lazy to implement it as an optional flag.
I want to. I don't see it because it's. So again, we have 1, 2s, and 3s. I save this as rim.nifty. Maybe let's call it scaled rim.nifty. And I open a new terminal in that folder, and I execute LM2 layers minus rim.
Oh.
You know what? I will make this much bigger again. Hope you can see it. SC rim. How do you have the number of layers?
NR layers.
NR layers. I don't know. Now let's push it 15.
Yeah, let's try the same to see the difference.
And minus. Let's just execute it. So this is now going through a big chunk of data. You can see how big the file is. It grows from inner and outer. Just equidistant.
Yeah,
I didn't select
it. Is the
yeah. So this will be the layers, right?
Yeah.
So now we can rename this and to layers.nifty, and again extract the profile LAYNII, the scaled. Let's start with the T1. So this is the T1. The number of layers are now much more flat, as you can see. The errors, the standard deviation has this dip here, which is usually kind of a dip in the L shape. So this is the tree of Chinari. It's usually closer to white matter as it is to CSF, in humans for that matter, and in rats it's the other way around. And as you see, it's in the T1 weighted images, the surface is darker. That's why the mean value goes down towards the surface. Let's do the same thing for the bold. AFNI, LAYNII, scaled, and bold. So we have more structure now in the bold tool. You see that we have this increase. Maybe there are some structures in there. Sorry, here I'm looking at the black line. Maybe there's a bump down there. That's something that Peter Koopmans described first, I think, in humans. And then obviously we have this huge peak of the superficial layers. But in bold, there definitely is some structure in there too, which we only see when we have these very small bin sizes and then many number of layers in the upscale space. Let's do the same thing in Vaso. And then AFNI, LAYNII, Vaso act. That's the wrong one. I used it complains now that the number of voxels doesn't match. I should use the same grid file for the layer file as I have for the Vaso. So I need to use the scale versions, the upscale version. And this is now the Vaso, which again shows the same number of voxels because it's using the same layers. It has more noise in the superficial layers, as always, but it does not have these huge peaks as bold has in the superficial layers. If you disregard this peak, you can still, you see this shoulder over there. That refers to the peak top, maybe in Vaso. All right, so this is basically how I do the layers. I upsample it quite a bit and then extract the layers not to have these biases. How is the time? I talked about 45 minutes, so maybe I make a short break and ask for questions and then talk about the different algorithms of layering for maybe 5 minutes. Do we have any questions about the upsampling? I'm sorry that I didn't really explicitly warn you that AFNI is very handy to have last session. In fact, I have a script that does the upsampling in LAYNII too, but that's in a very old version of LAYNII using Odin libraries. So maybe that's also something to have in, because it's so simple to have to include in LAYNII an upsampling. Yeah.
So upsampling can also be done using FSL flirt, apply ISO XFM flag, if people are familiar with that. Or for Python people, you can use the SciPy and image module and the function zoom to upsample. There are similar functions for MATLAB too, for MATLAB users. I mean, this is just like a one researcher's way of doing it, right? This is not the way of doing it. Like you can choose your own way of extracting the layers and plotting them in the way that you like.
And if you upsample, this allows you to generate more layers. So for example, when we have, like when we don't upsample, the layers need to be thicker in order not to be rank deficient. This means that we're also picking up signals from voxels across a wider range of cortical depths. So we have basically doing a histogram with a larger bin size. And then therefore, yeah, we always smooth more and lose a bit of resolution. However, we must keep in mind that the number of data points that we have on our x-axis here does not represent the resolution that the fMRI gives us. Yeah.
Any questions from anyone? Or maybe the part that you didn't follow or understand?
I have a question. So far, you've just drawn a single layer or rim profile on a single 2D slice. If you did it, in 3 dimensions, so if you did layers across multiple slices, would everything still work, or is there a different processing stream needed?
That's a very good question. In fact, for the I had it. Sorry, I need the other window. For the LN2 layers, it does not have any differentiation between
2D and 3D.
2D and 3D. So if you run this with 3D data set, it does it just the same. If you use the grow layers, you would need the minus 3D flag, which it doesn't find the rim file now.
Yeah.
Let's see.
Named it.
Yeah, right. So this does it. If you have the 3D flag, then it does it in 3D, which takes a bit longer, of course. But
makes sense. Okay, cool.
And this is in fact very handy. Like often when you draw it across the different slices, you don't really have the same borderline across the different slices. And as soon as you do it in 3D, it kind of averages out the slices in the third dimension. Like, I would. There's no reason not to do it in 3D. In fact, if you run the 3D flag, even if you have a 2D slice, it should give you the same thing.
Okay, cool.
All right, and let's look at the difference between equivolume and equidistance. So we have the rim, the LN2 layers rim with. Why do we have only 5 layers? I will go back.
Yeah.
There we go. No.
Isn't it in the other bash terminal? I think you changed terminals.
But I'm in scale, right? So it should be LN2 rim. No, I will just.
No, it's in the other terminal, Renzo. Switch to the other one.
There it is. Thanks. So we use the minus equivolume flag. Or how do we call it?
Equivol.
Equivol. There it is. Equivol.
So now it will do something extra to also give you equivolume layers. Should we talk about the difference between equidistant and equivolume layers? Like, is everyone familiar with this?
I was going to show it on the results of that stage.
Yeah.
And
like what do we mean by equivolume? That's what I was saying. Because this is such a discussion, right?
So this is layers. And we have to say for equivolume. Is it not done yet? No, it's coming.
I will make this faster. It's too slow.
Oh, don't worry. It's fast enough. Don't waste time. So this is the same thing for equivolume. use the same color code. I think I used that one. So here you see the difference. So the biggest differences are happening kind of right around there, where we have a sharp curvature, and also here, where we have a sharp curvature. And I can stop sharing my screen, and Farouk, you show how you explained it on your blog post. Or I will just show it. Like there are two blog posts that I linked on the summer course webpage. Maybe I show you my version of it. So there is this physiologist, Bock, who said that the certain layers are at different cortical depths depending on the curvature. And there are different ways of how you reconstruct it. And maybe I can show you this animation. So there are different algorithms on how you estimate the depth of a certain cortical layer. Before I say more about it, I want to show you the final results that usually it really doesn't matter. So don't lose too much.
For our current image resolutions, what he means, right?
So we have like different algorithms implemented. The layer profiles should look the same at up to like at least 700 micrometers. Yeah. If you go to very high resolution, like Valentin Kemper did, then you might see these tiny little biases. If you go to even higher resolutions, then maybe it might even matter more. These, yeah, for us, it doesn't matter. Yeah. But we have it in there anyway, because theoretically it's more close to the ground truth, but it also has a lot of trouble. And namely, it kind of amplifies noise. For example, if you look at the equivolume and equidistant layer, the equivolume layer kind of amplifies segmentation noise that we have. It also amplifies kind of these voxel steps that we usually have. And it also is not really well defined on how you define the volume that the layers should be equally distributed across.
Yeah.
And then sometimes, as we actually see in this data set too, that if I really zoom in, you see that here the deepest layer, layer 1, is only thick enough to be like distributed across an entire voxel around this patch. Right over there, we start with layer number 2, right? And then layer number 3 is only like every now and then. And here at this part where we have a very sharp curvature, we even start with layer number 3, because the other ones are just so tiny little thin that we miss them. And at the borders between different curvature radii, we then have these jumps in there. So for the resolutions that we are interested in, I would actually recommend you not to use the equivolume approach. You can also always kind of account for these issues by using different smoothing, which happened like here with the smoothing iterations. You can adjust the smoothing by iter smooth. For example, the default is 100. If you choose iter smooth,
there's one extra letter though.
1000. This will take a while, but then I will show you the result. So you will see that some of these issues go away. But then, of course, we kind of smooth out the curvature, which means that the benefit of the equivolume is kind of gone away anyway. So we're kind of making the equivolume more like an equidistant approach, because the curvature is like eventually, if we smooth infinitely like wide, then obviously the curvature will be gone away, and then everything's at the same. Like it will converge with equidistant approach at the end. I might have overdone it now. Is there anything you want to add, Farouk?
I would like to add the metric output that like I decided to put as a default output, because like some of these issues are related to how many layers that we want, 3 to 5 to 15 to 100, but actually for each voxel, you can just write the normalized cortical depth value measured for that voxel. So which means that you basically stay in a more like a continuous measurement case for all of these voxels, because like when you want a predetermined number of layers, you need to quantize this normalized cortical depth into a certain range of integers. But if you use just the metric, like measured for each voxel without quantization, now you can maybe use scatter plots instead of line plots to plot your layer profile as a scatter plot. And this idea was like, first I discussed with Martin Havlicek, and then I discussed with Kendrick Kay, and they were supportive of this idea. And maybe like we will write something about it in the future. Like, what is the difference between the line plot with changing the number of layers desired versus just a scatter plot with, yeah, exactly, with all the values between 0 and 1 and not quantized into a predetermined number of layers.
Which is the original way how I think the very first layer FMI from Ravi Menon did it, I think.
Yeah, I mean, which makes sense, to be honest. And it avoids quite a few problems about quantization.
And eventually, if implemented correctly, it might even avoid the upsampling altogether. Yeah. So you just look at
I think so too.
Bin different delta X values into certain layers afterwards.
But maybe one takeaway is that like there are quite a few decisions that one needs to take in terms of like how to determine the layers, equivolume, equidistant, how do you extract it, how do you plot it. And I think like for some of these decisions, like the jury is out there still a bit. Like, so you can like do not think that like one way is the way of doing it, and try to think about it, try to judge for yourselves like all these decisions. We wrote like 2 blog posts about it, so like go ahead and read them, because they are going more into detail and giving some references too for further reading. And maybe you will realize something that we were doing wrong, and you will fix it. And let us know, hopefully, too.
Also on Farouk's blog post about the avocado toast, he really explains how the algorithm works. So he uses, like, with little intuitive animations, he describes how he uses the flooding from different ways, and then uses the average and the proximity relationships to estimate the cortical distance, to get streamlines, to get columnar definitions, and also the mid-gray matter. Do you have the mid-gray matter somewhere? No.
Yes, yeah. It is there after this one, I think.
All right.
Yeah. Here the yellow one is the mid-ground.
And here maybe you see better how the equivolume approach, physiologically speaking, best matches the layers. So here you see in this ex vivo data set from Ding et al. How the dark line here, the sphere of Gennari, is kind of closer towards the red line at the top of a gyrus, and deeper at the bottom of the sulcus. And the green version, which is, I think, even overemphasizing the equivolume approach, which is Farouk's way of doing equivolume, it fits the best here, compared to, for example, the yellow line, which would be the equidistant. And Farouk even applied this to the, I think this was 0.1 millimeter whole brain, big brain, and it took, how long did it took you?
I think
12 minutes.
Like I think 100 micron. I forgot to put it there. I think it took like 1.5 hours or something, which I will make faster. I mean, it's basically like we are not limited by the processing time, or maybe a little bit limited by the RAM for now. But yeah, if you want to just upsample some of your images, not all of them, maybe your anatomical into 0.1 millimeter isotropic resolution, like whole brain, and then if you also upsample your segmentation file to 0.1 millimeter isotropic, you can, in a practicable times, you can get the layers by using LAYNII. LN2 layers, and do whatever you want. So like our idea is that we want to have always the 2D option available, and partial coverage, like all the programs should work there, and also the programs should work for the whole brain coverage too. This is our approach. And we try to always make the commands the same across all these different images, like 2D image, partial coverage, very small region of interest image, or a whole brain image at several resolutions.
So in the meantime, the smoothing thing worked with 1000 steps. And now you see that this problem of having the kind of the missing orange voxels over there has gone away. And also the fact that layer number 1 was only visible at a few voxels has partly gone away. So now we have more layer 1. At the bottom of the sulcus, we still don't. You could solve this by reducing the number of layers. Here, I think we had 15 or 14. 15, yeah, or increase the smoothing. But eventually, you will converge to the equidistant. So now if I switch back and forth between the equivolume and equidistant, it's not that hugely different anymore. And when you have a straight patch of cortex, like for example, focus on this part, then both algorithms give you the same answer, basically.
Which they should.
All right, are there any questions? All right, then I stop recording. And maybe